This presentation is part of a lecture series on multi-resolution signal and geometry processing by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series, as well as the corresponding textbook, can be downloaded from the website whose URL is given on this slide, in particular this URL here. Having looked at the OpenGL and GLUT library on the earlier slides, we're now in a position to look at some actual example programs using OpenGL and GLUT. So this is what we're going to look at in the next several slides. The first program we're going to look at is called Simple2D, and it's just a simple 2D graphics program, as the name suggests. It draws a point, a line segment, a triangle, and a quadrilateral, and the graphics output looks something like what's shown in the figure on this slide. At this point, I'll give a quick demonstration of the Simple2D program. So when I run the program, and by the way, this minus geometry option is just so that I can control where the window is placed, so that it will be placed in the part of the screen where I'm doing the video capture. When I run the program, it pops up a window. It clears the window background to black and then draws a variety of geometric shapes in a variety of colors. The application handles window reshape events, so if I resize the window here, you'll notice that when I resize the window, the aspect ratio is maintained. Even if I make the window very rectangular and elongated in one direction, still the square looks square. The aspect ratio is maintained regardless of how I resize the window. And this is because I'm correctly handling this inside the application. It doesn't happen magically by itself. And the only other thing we can do with the application, we can type the Q key, the lowercase q, which will quit the program. Now I'm going to give a walkthrough of the source code for the Simple2D program. This program consists of a single source code file called simple2d.cpp, which is the file that we're looking at now. And I'm going to start with the main function on line 99. So if you go to line 99, the first thing we do in the main function is initialize some constants that specify the nominal window width and nominal window height for any windows that are created later. Then we initialize the GLUT library by calling GLUT init. This will also have the effect of parsing or extracting any special command line options used by the GLUT library, such as the minus geometry option. Then we proceed to call GLUT init display mode to specify the display mode for any new windows that are to be created. And we're enabling or choosing double buffering, so any new windows that we use will use double buffering. And we're also using RGB color, so they're going to be windows that use color. Then we proceed to call GLUT init window size to specify the nominal width and height of any new windows that are created. Again, this is just a nominal size. These values don't have to be respected, so it's really important that you actually check what the size is of the windows when the program runs, and not just assume that they're using the size that you have specified here. And if we scroll up a little bit here, the next thing we do is we call GLUT create window to actually create a new window, and we pass it a string which is just the title for the window, which typically appears in the title bar at the top of the window, but again, this will depend on the particular operating system and window manager that you're using. Then we start to register callback functions for various different events. The first one is for the display event, so we call GLUT display func, and we tell it that we want to register our function called display, which appears on line 16 much earlier in the file. This is the function that's to handle display events. Then we register a function to handle reshape events, and the function is called reshape. It appears on line 61, and we'll look at it in more detail in a moment. Then we register a callback function for keyboard events, and the name of the function is called keyboard. This appears on line 88, and we'll look at this in more detail in a moment. Then we call GL clear color to specify what's the color to be used when we clear the windows, clear graphic windows. And this is specified in terms of an RGB alpha value. So RGB values of 0 correspond to black. And since we're not using alpha, this is basically going to be ignored anyway. Alpha is for transparency information if you're doing blending. And then we call GLUT main loop. And this function will never return. GLUT main loop enters the main event processing loop inside the GLUT library. And all that function does, essentially, it waits for an event to occur. When the event occurs, then it will call the callback function that you have registered for that event. And then it goes back to sleep waiting for another event. And it just loops doing this forever. So now let's look at some of our callback functions, which is where most of the work of the program is done. So to begin with, I'll look at the reshape function, because this is the first function that would be called. You're guaranteed by the GLUT library that before the first time your display callback function is called for a window, the reshape callback function will be invoked first, at least presuming that you've registered a callback for the reshape event. So when this callback is invoked, it's passed two parameters, which is the width and height of the window, basically what the window has been resized to, or if it's the very first time the function's being invoked after the window's been created, it tells you the actual size of the window initially. Then we do some computation to calculate the aspect ratio for the window, because we want to adjust the shape of things so that the aspect ratio is maintained even when the window might be very elongated in one direction or the other, so that squares look squares and circles look circular as opposed to elliptical. Then we initialize the viewport, which is the portion of the window that we actually want OpenGL to draw into. And we're specifying essentially the whole window here. In this application, we're going to draw into the entire window. Then we set up our projection matrix. So before we can do this, we need to set the matrix mode to say that the particular matrix we want to be modifying is the projection matrix as opposed to the model view matrix. Then we initialize the matrix to the identity matrix. So the projection matrix will be initialized to the identity matrix. And then on the next few lines, we initialize a 2D orthographic projection. Since we're only doing 2D graphics, this is relatively simple. We don't need to deal with any sort of three-dimensional projection transformation. And there's two cases depending on whether the window is wider than it is tall or taller than it is wide, which correspond to these two cases of the if and the else. Then as we proceed along here, we then set the current matrix to the model view matrix, and we load it with the identity matrix. And that's all we're going to do here. We're not going to do anything more fancy with the model view matrix. And then this function returns. And then most likely the next thing that's going to be invoked would be our display callback function, and this appears on line 16. So if we go to this function, the very first thing we do inside the display callback function is to clear the window, because we don't want any old stuff that's appearing in the window to mess up the stuff that we're currently drawing. And when we clear the current window, there's two types of information that we can clear. We can clear the color buffer, which is the actual color information that we're drawing. We can also clear the depth buffer, which is the Z information about the pixels that are drawn. And typically you always want to clear the depth buffer. If you don't do this, unless you're doing more fancy stuff and this is really your intention, the effect will probably be a bug where some things won't get drawn due to depth buffering. So you almost always want to clear both the color buffer bit information and the depth buffer bit information. Then we proceed to actually draw the geometric primitives that this program actually draws. First we draw a point. So we first set the point size to control how large the point's going to be appearing when it's rendered. Then we call GL begin, and we specify as a parameter GL points, which says we're going to be specifying a bunch of points using GL vertex function calls. And first we set the color for the point. We're setting it to equal amounts of red, green, and blue, which is going to correspond to something which is gray. Since it's full red, full green, and full blue, in other words, the maximum values of 1, this will correspond to white. Then we draw our vertex at the coordinates 0.25, 0.75, and then we call GLM to say that we're done drawing points. Then we proceed on to draw a line. Before we do this, we specify the line width. Then we call GL begin, specifying a parameter GL lines, which says now we're going to give pairs of vertices, which correspond to the two endpoints of line segments. Before giving any vertex values, we specify what the color is for the vertexes, or for the line that we want to draw. In this case, the amount of red is 0, the amount of green is full, and the amount of blue is 0, so this is going to be bright green. Then we specify the two endpoints using two GL vertex function calls. So one endpoint will be 0.6, 0.25, the other endpoint will be 0.9, 0.25, and then we call GLM to say that we're done drawing line segments. Then if we proceed along here, the next thing we do is we draw a triangle, and to begin with we call GL begin, specifying a parameter of GL triangles, which says we're going to provide sets of 3 points which correspond to triangles. Before giving any of the vertices, we set the color. to like maximum red, no green, and maximum blue. Then we proceed to give the 3 vertices of the triangle, which are 0.6.6, 0.9.6, and 0.9.9. And then we call GLN to say that we're done giving vertex information to OpenGL. Next, we draw a quadrilateral, so we call GL begin, and we specify as a parameter GL quads to say we're going to be giving sets of 4 vertices that correspond to quadrilaterals. Before giving any vertices, we set the color to be no red, maximum green, and maximum blue. Then we give the 4 vertices for the quadrilateral, 0.1.1, 0.4.1, 0.4.4, and 0.1.4. And then we call GLN to say that we're done drawing providing the vertices for quadrilaterals. And then the very last thing that we do inside the display callback function is called glut swap buffers. And this is really important if you're using double buffering. A very common mistake for people who are kind of newer to graphics programming is they forget to call swap buffers. Remember that when you're using double buffering, and when we initialize the display mode back at the beginning of the program, we enable double buffering. So this means that there's 2 full copies of the window. One that you're actually drawing into that the user can't see, and one that you're not drawing into, which is the one that the user does see. And what glut swap buffers does is it takes the window that you're currently drawing into that the user can't see and swaps it with the one that the user can see. So in effect, they will now see the graphics that you've actually drawn. If you don't call glut swap buffers, then nothing will ever actually appear visible to the user. You're happily drawing away very beautiful graphics in a buffer that nobody can see. Then the last callback function we have in our program is on line 88. It's the keyboard callback function. And this program allows you to quit by typing a lowercase letter q. So this function will be invoked anytime a key on the keyboard is pressed, and one of the parameters it passes in is the key that was actually typed. It also passes in the x and y coordinates of the mouse position, because sometimes you might want the behavior or interpretation of what the key means to depend on where the mouse is in the window. In this case, we're just ignoring it, the position of the mouse. So if the key value is equal to q, a lowercase q, we just call exit to terminate the program. And that's basically the whole program. Next, we're going to look at the Simple 3D program, which rather unsurprisingly is a Simple 3D graphics program. And essentially what it does is draws and animates several simple polyhedra, and the graphics output looks something like what's shown on this slide. At this point, I'll provide a quick demonstration of the Simple 3D program. And on the command line that I'm typing, I'm going to use the -geometry option just to force the window that's created to be placed at a particular position on the display. As you can see, this particular program creates an animation effect. And I can increase and decrease the frame rate by typing uppercase F and lowercase f. So if I hit uppercase F repeatedly, notice that the rate at which the animation is occurring slows down. On the other hand, if I keep pressing lowercase f repeatedly, then the speed of the animation increases. In other words, the frame rate that's used by the application increases. I can also change the window size, and it properly handles the change in the window size so that the aspect ratio is maintained and the shapes of the objects don't get distorted even when I make the window very elongated in one direction. I can use the left arrow, right arrow, up arrow, down arrow, and page up and page down in order to change the vantage point of the scene. If I use the down arrow, it changes the vantage point in this way. If I use up arrow, it changes it in this way. If I use right arrow, change in this way, left arrow changes in this way, page up, if I press it repeatedly, page down. And the only other thing the application allows us to do is quit by typing q, lowercase q. Now I'm going to give a walkthrough of the source code for the Simple 3D program. This program consists of a single source code file called simple3d.cpp, and this is the file that we're looking at now in my editor. So to start out with, there's some global data that's used by the program. There's a variable called frame period, which is the period with which the graphics output is updated in milliseconds. So essentially a new frame is drawn every 33 milliseconds. The next parameter, theta, is used to animate the polyhedra that are drawn in this program. If you remember what the program looks like when you run it, it draws a bunch of polyhedra, and they're rotated by different angles as the program's running. So theta determines the rotation angle, and as the program runs, this parameter is varied. Then there's three parameters, I0, I1, and I2, and these affect the vantage point from which the scene is viewed. In other words, they affect the eye position in various ways. So these are the global data used by the program. Now I'm going to skip down to the main function on line 313 and look at what happens when the program first starts up. So to begin with, we set some constants, wind width and wind height, which are the nominal window width and window height that are used later when we create a window. Then we proceed to call glut init. Again, glut init has to be the first function called in the glut library because this performs any initialization that's required by the library. In addition, this function will extract out any command line options that are related to glut from the options that are provided to the program using the argc and argv parameters that are passed here. Then we call glut init display mode to initialize the display mode. So in this particular case, we're going to enable double buffering, or choose double buffering for any new windows we create. We're going to use RGB color, so we're going to be doing the graphics in color, and we're going to request the windows support depth buffering. Then we proceed on to specify the nominal window size for any new windows that are created using the function glut init window size, and we pass in wind width and wind height as parameters that were the constants that we initialized above. And if we scroll up here, the next thing we do is we call glut create window to actually create a window that we can draw into, and the parameter that's passed here is just a string which is indicating the title for the window. Typically the title appears in the top title bar that appears on the window, although this varies from operating system to operating system and window manager to window manager, but this is typically what you see. Then we proceed to register callback function. So first we call glut display func to register a display callback function, in other words a callback function to handle display events. This is what actually does the drawing in the program. Then we call glut reshape func to register a reshape callback function. This handles window resize events for our program. Then we register a callback function for keyboard events. This is just regular keys, things other than, for example, other than things like arrow keys and page up, page down, and so on. And then we register a special keyboard callback function. This handles things like arrow keys, page up, page down, things like this when they're pressed on the keyboard. And each of these callback functions, display, reshape, keyboard, and special, we'll look at in more detail momentarily. As we continue along in the main function, the next thing we do is we set the clear color. This is the color that windows are initialized to when they're cleared. So we're setting the RGB values to 000, which is black, and the alpha value we're not actually using here because we're not using alpha. Then we proceed to call GL enable to, basically the next few steps, we want to initialize some of the OpenGL state. And one of the things we want to do is we want to enable depth testing or depth buffering. So although when we initialize the display, when we call GL init display, we specified we wanted to have access to depth buffering. This doesn't actually necessarily turn it on. It just says that we want the window to support it. This GL enable function call is saying we want to turn depth buffering on. So it's important to make sure that depth buffering is turned on. So this is what we're doing here. And by default, I believe it's not turned on. So this is actually required. Then we set some more OpenGL state. We set the GL call face option as being enabled. This just says that we don't draw backside of faces. Every polygon that we draw has two sides, the front and the back. This is just saying don't draw the backside, which in many cases you don't want to draw because you don't really care about the backside of polygons in the first place. Then we proceed to call GL shade model. There's different ways that we can perform shading. When you draw a polygon, for example, you can specify different colors for the different vertices of the polygon, and you might want to do some kind of smooth interpolation of these colors across the face. And this is what GL smooth does. There's other types of shading that we can use as well, but in this particular case we want to use smooth interpolation. Then we specify the orientation for front-facing faces, as counterclockwise. This is what this is here. And then we register a timer callback function. So the function that will be called is the function timer here. And we'll look at the timer function in more detail later. The variable frame period is specifying how long before this timer elapses or timer expires. This is essentially how long it will be before our callback function gets called. And then 0 is a parameter that will be passed into our callback function when it's invoked. We don't actually use this value, but this can be useful if you have multiple timers so that you can distinguish between which timer actually expired. And then the last thing we do is we call glut main loop inside the main function. And again, glut main loop never returns. It enters the main event processing loop inside the glut library, which waits for an event to occur, and then when the event occurs, it processes it by calling whatever callback function the user has registered, and then it goes back after the callback function returns, then it waits for another event, and so on. It just keeps looping like this. So the next thing I want to look at is going back to near the top of the source code file. I want to look at the function degree to radian. This just converts from degrees to radians because OpenGL likes to specify everything in degrees, but almost everything else, radians is more convenient. So this is just a helper function to convert from degrees to radians. The next function I want to look at is draw axes. What this does is it draws x, y, z and coordinate axes in certain colors with certain dimensions and so on. So if we look at what this function is doing, we first of all set the line width because we're going to draw a bunch of line segments, and then we say GL begin, specifying as a parameter GL lines, which says we're going to provide pairs of vertexes which correspond to endpoints of line segments. And essentially what we're going to do is draw the positive and negative x-axis, the positive and negative y-axis, and the positive and negative z-axis, and they're all in slightly different colors. So to begin with, we do the positive x-axis. So first we specify the color, because at the point when we say a GL vertex, it will use whatever the current color is. So before we call GL vertex functions, we need to first set the color. So we set the color to an RGB value of 100, so this is going to be bright red because the first number here is the amount of red in the color. And then we draw a line segment from the origin 000 to length 00. So this is going to be corresponding to the positive x-axis. And then we do a similar thing for the negative z-axis. The main difference is the coordinates, of course, and also the color. We draw this in slightly darker red because it's not 1.0 for the red value, it's 0.5, so it's a little bit darker, a little bit less bright. And if we scroll up here, we move along to the positive y-axis next, which is this code here. It's a similar sort of pattern. We set the color first, then we do two GL vertex calls to specify the coordinates for the line segment. And the negative y-axis, we set the color, then draw the two vertices, the positive z-axis, and then the negative z-axis. And at the very end, we're very careful to remember we have to call GL end. For every GL begin function call, there has to be a GL end, otherwise bad things will happen. So we call GL end, and then this is the end of the draw axis function. So this basically drew our coordinate axes. Then if we scroll up here, I want to look at the draw tetrahedron function next. So this, as the name suggests, this draws a tetrahedron. And just to make the function a bit simpler, it's table driven. So it has a bunch of data entered into arrays. So the coordinates of all the vertices for the tetrahedron are entered into an array. And then the neighborhood relationship between faces are entered into an array. And also the colors for the different vertices are also entered into an array here. So this just makes the code that actually draws the tetrahedron much simpler. Instead of having many calls to GL color and GL vertex, instead we can just do things with a loop, which is basically two nested loops here, which makes things a lot simpler. We have a single GL color call and a single GL vertex called inside of a loop. So what we do to begin with is we call GL begin and specify that we want to draw triangles because each face in the tetrahedron is a triangle. And then the outer loop here is looping over each face, this loop here, and then the inner loop is looping over each vertex for the given face. So in the inner loop here, what we do is we get the index of the vertex in the particular face that we're drawing and assign it to V. Then we look up in our array of colors what the color is for the three vertexes or the color, the RGB color are for the vertex that we're about to draw. So this is the red component here, the green component here, and the blue component here. So we set the color, then we actually draw the vertex by looking up in the vertex array what the x, y, and z coordinates are for that particular vertex, and then we just loop, and we do this for all of the vertices that we have to draw. So this is the draw tetrahedron function. The next function is the draw star function. This is what draws, if you remember, there's one thing that kind of has a star shape. It's kind of like two overlapping tetrahedrons that are oriented differently with respect to one another. So if we look at this function, draw star, what we do to begin with is we set the current matrix to the model view matrix, and then we save the current model view matrix by calling GL push matrix. This pushes it onto a stack, and then later we can restore the value that we saved by pushing with a pop operation. Then after we've done this, we just draw a regular tetrahedron without doing anything fancy, using the function we just looked at. But then what we do next is we want to draw a second tetrahedron that's rotated with respect to the first, because the way that we get the star shape is by drawing two tetrahedrons, but they're rotated with respect to one another. And in particular, what we want to do is we want to rotate the second tetrahedron by rotating about the x-axis, which is what these coordinates here give. This is a vector which corresponds to the x, y, and z component of an axis of rotation, and we want to rotate 90 degrees. So it's going to rotate 90 degrees about the x-axis, and then we're going to draw a tetrahedron. And the reason why this achieves a different effect is because draw tetrahedron just uses whatever the current coordinate system is. So since between the time when we drew the first tetrahedron here and the time we draw the second tetrahedron here, we've transformed the coordinate axis by rotating them by 90 degrees. So the second tetrahedron that's drawn will be rotated with respect to the first. Then after the second tetrahedron is drawn, then we want to be careful to restore the model view matrix to what it was before, because we don't want to draw everything else for the whole remainder of the program to be rotated by 90 degrees about the about the x-axis due to this rotate operation here. So we restore the model view matrix. So this is the draw star function. Then the next function I want to look at is the reshape callback function, because this is most likely the first callback function that's going to be invoked. Again, you're guaranteed that the reshape callback function will always be invoked before the very first time the display callback function is invoked for a particular window. So the reshape callback function, again, it has two parameters, the width and height, which indicate what the width and height of the window is. If it's being resized, this is the new width and height. If it's the very first time that the window is actually going to be drawn, it's just been created, and this will indicate the initial width and height of the window. Inside this function, the first thing we do is compute the aspect ratio for the window to try to figure out how we want to adjust things so that the aspect ratio of what we draw will be correct. In other words, squares will look square and circles will look circular and not elliptical. Then the next thing we do is we set the viewport, the portion of the window that we're going to draw into, and the choice that we're making here is essentially to draw into the entire window. We're going to use the entire window for drawing. Then we proceed on to set the projection matrix. So we have to set the current matrix to be the projection matrix. So we're saying we specifically want to update this particular matrix. Then we load it with the identity matrix to begin with. And then we call glue perspective. What this function does is it multiplies the current projection matrix by a perspective matrix transformation. And the parameters of this perspective transformation are the parameters here. For example, 1 and 1000 are the near and far clipping planes. The z coordinates for the near and far clipping planes. Then after we're done, we want to set up the model view matrix. So we call GL matrix mode and set the current matrix to be the model view matrix. So all of the changes that we make subsequently will be to the model view matrix. And we simply load this matrix with the identity. We're not going to do anything fancier than that. The other manipulation of the model view matrix will be done at the time that we're drawing. So now if we go to the display callback function where the actual drawing is done, this is on line 141. If you look at what happens here, the very first thing we do is we call GL clear to clear the contents of the window. And again, you almost always want to clear both the color and depth buffer information. The color information for obvious reasons, the depth buffer information, because if you don't clear this out, this is essentially the Z information, the depth information, then some things that you draw may not appear because they're thought to be behind something that's already drawn. So you almost always want to clear the depth buffer information at the same time you clear the color buffer information. Then we proceed on. We call GL matrix mode to set the current matrix to be the model view matrix, because we're going to want to perform some manipulation of the model view matrix in what follows. Then we call GL push matrix to save the current model view matrix. So we're going to make a whole bunch of changes to the model view matrix, and at the very end we want to restore the matrix to what it was previously. So we're going to push the matrix onto a stack, and at the end we're going to pop the old value off of the stack that was saved. As we proceed along here, the next thing that we do after we've saved the current model view matrix with GL push matrix, we're then going to multiply the current model view matrix by a transformation that's produced by the function glueLookAt. What this does is it sets up a transformation that makes it appear as if the eye or camera is sitting at a certain position in space with a certain orientation. And these parameters here are basically specifying the position and orientation of the camera or eye. And these values here are being computed from I0, I1, and I2, which, if you remember from much earlier in the program, these are global variables that control the vantage point for the scene. Then after we set up this transformation using glueLookAt, then we start drawing stuff. So we call draw axis to draw the coordinate axes. Then we proceed along here to draw the star-shaped polygon, which appears at the origin. If you remember, there's a star-shaped polygon that appears at the origin of the scene. In order to do this, we first call GL push matrix to save the current model view transformation matrix, because we're going to modify it, and we want to be able to restore it to what it was previous to these modifications. Then we apply these transformations here. This is basically going to rotate about the y, rotate about the x, and also scale things. And then we're going to draw the star using the draw star function. The reason for applying these transformations here is that the draw star function always draws the star centered at the origin with a specific orientation and a specific scale. And the orientation and scale is not what we want. But what we can do is, before we call draw star, we can apply a coordinate system transformation so that draw star will be kind of effectively tricked into drawing things with the correct rotation and scaling that we want. Then after we've drawn the star, then we call GL pop matrix to restore the model view matrix to what it was at the point when we pushed it up above on this line here. Then we proceed on to draw the tetrahedron that appears on the negative x-axis. So we have a similar pattern here. We call GL push matrix to save the current model view matrix. Then we apply some transformations here to change the position and orientation of the coordinate axes, so that when the tetrahedron gets drawn on line 175, it will be drawn at the right position in space with the right orientation. So essentially what we're doing here is we're applying a rotation about the x-axis, a scaling, and then a translation by minus 1.5 along the x-axis. So this is going to move the object down the x-axis so it will appear on the negative part of the x-axis. And then we draw the tetrahedron, and then after we're done, we're careful to restore the model view matrix to what it was before by calling GL pop matrix here. It gets restored to what it was at the point where we call push matrix on this line 171. Then we proceed on to draw a tetrahedron on the positive x-axis, and the pattern here is exactly the same as what we had for drawing the tetrahedron on the negative axis. The only difference is we have a slightly different transformation taking place here, especially that the translation is by a different amount. Then we draw the tetrahedron on the negative y-axis using a similar piece of code here. And if we move along, use a similar piece of code to draw the tetrahedron on the positive y-axis. And then after we're all done this, if you remember, we called GL push matrix very close to the top of this function. So now we call GL pop matrix to restore the model view matrix to what it was. And you always have to have the pushes and pops match up. You don't want to keep pushing stuff onto the stack without popping it. If you do this, eventually you'll overflow the stack. And then lastly, in the display function, we call glut swap buffers. Again, this is critical because we're using double buffering. This means that all of the drawing we're doing is into a buffer that the user doesn't see. And if we actually want to swap the buffer so that the buffer that we're drawing into becomes the buffer that the user sees, and the buffer that the user sees becomes the buffer we're drawing into, we have to call glut swap buffers. If we don't do this, then the user will never see anything change. We'll be drawing lots of beautiful graphics into a buffer in memory that nobody can actually see. Then if we continue along, the next callback function I want to look at is the keyboard callback function on line 237. So this keyboard callback function needs to process 3 different keys. Capital F allows us to decrease the frame rate in the program, the rate at which the screen is updated or window is updated. Lowercase f increases the frame rate, and then Q terminates the program. So again, the keyboard callback function, it gets 3 parameters. The first is the key that was typed, the letter that was typed, or character. And then x and y are the x and y coordinates of the mouse. In this program, we don't care what the x and y coordinates of the mouse are. In some programs, you might want to use the x and y coordinates to change the meaning of what the key is. If the mouse is in a certain position on the screen, a certain key might mean one thing, but if the mouse is in a different portion of the window, maybe the key will mean something else. But in this particular case, the meaning of the key doesn't change depending on what the mouse is, so we simply ignore the x and y parameters to this function. Then we do have a switch statement, switching on a key. So in the case of capital F, what we do is we increase our variable, which is the value for the frame rate in milliseconds, so we increase it by 1 millisecond. And then the next thing we do, which is very important, is we force a display event to be generated. If we didn't call glut post redisplay here, which forces a new display event to be generated, then nothing would change in the graphics window, because incrementing the frame period doesn't cause anything to change. As far as glut is concerned, it does no way to know what the semantics of changing the frame rate is. When we decrease the frame rate, maybe it means that we should have redrawn things. So to be safe, we force a display event to be posted to redraw the window. In the case that we increase the frame rate, basically we do a similar thing. We adjust our frame period, making sure that it doesn't go below 1. We don't want to decrease it down to 0, so we use max function here to ensure that we don't go below 1. And then we call glut post redisplay to force a display event to be generated. If the user types Q, we just terminate the program by calling exit. Then the next callback function I want to look at is the timer callback function, this one here. So the timer callback function, it has a single parameter that's passed in, which we don't actually use in this particular case. This can be used, for example, if you use multiple timers in your program and you need a way to distinguish between which timer is this event being generated by, this parameter can be used for that purpose. Since we only have one timer in this program, we know which timer is expired. And when the timer expires, what we do is we take our theta variable. This is a global variable which controls the rotation angle for the different polyhedra in the animation, and we add 3 to it. It's basically adding 3 degrees to the rotation. Then we call glut post rate redisplay, because when we change theta here, this means that the graphics output will now look different. But there's no way for the glut library to know that the output will look different, because it doesn't know it has no way to know we changed something in our program which will affect the display. So in this case, we actually need to generate a display event ourselves. Sometimes display events are generated from external agents. For example, a user has a window covered up and then they uncover it, and now we need to draw into it because it's become exposed, it's become uncovered. So display events are often generated by things external to our program. But in this particular case, there's something that we've changed internal to the program, and now we know that this means the display will look different. So now we have to force a display event to be generated, because unless there's a display event generated, our display callback function won't be called, and if our display callback function is not called, nothing gets drawn. So this is the reason for calling glut post redisplay here. And then at the end, we call glut timer func to register a callback function for the timer event again, because these timers are a one-shot deal. So once the timer expires, that's it. You'll never get another timer event. So if you want another timer event to be generated, you have to restart the timer by calling glut timer func. And again, we provide the time period for the timer is just our current frame period. The function to be called is the function that we're actually in now, timer. And this value we don't actually use. This is the value that would be passed in here, but we just ignore it anyway. Then if we move on to the last callback function, which is the special callback function, This is the function that handles special keys like up arrow, down arrow, left arrow, right arrow, page up, page down. These are all used by the program. So the first parameter that's passed in is an integer value, which is used to indicate which particular key was pressed. For example, for a left arrow, it's glut key left. And then x and y are the x and y position of the mouse, because sometimes we might want the meaning of the keys to change depending on the mouse position. In this particular program, it's irrelevant where the mouse is placed. We don't care. The key always means the same thing, so we just ignore the x and y value. In the case that the user types the left arrow key, then we're going to execute the code here. So that what we do is we take the global variable called I1, which affects our vantage point for the place where we're viewing the scene from, and we adjust this value by subtracting 1 from it. And then we are careful to call glut post redisplay, because again, any time that we change something, it affects what the graphics output will look like, and this change here will affect that because it's moving where the eye is or where the camera is. We have to be careful in this case to call glut post redisplay to force an event, a display event, to be generated. Because again, if we make changes internally to what the graphics will look like, glut has no way to know that this has happened. So we have to tell it that this has happened by forcing it to generate a display event for us, and this is what glut post redisplay does. A very common mistake to make in programs is you forget to call glut post redisplay, and then even though the graphics output for your program has changed, there's no display event generated, and then the screen doesn't get updated. And then we do a similar thing for each of the remaining keys. Glut right key, we basically adjust some parameter, call glut post redisplay. Glut key down, similar thing. We adjust some parameter and then call it glut post redisplay, and so on. The only difference between how we handle the different keys is in the case of each key, like glut key left, we're adjusting I1, glut key down, we're adjusting I0, glut key page down, we're adjusting I2, but basically the pattern is similar. And in some cases we're incrementing values, other cases, like for example here, we're incrementing a value, here we're decrementing a value, but otherwise the code looks very similar. And that's basically it. The next example program that we are going to consider is the cube program. This program demonstrates 3D graphics with a light source. The program draws a cube with the various faces of the cube having a variety of colors, and the cube is illuminated by a single light source. The graphics output of the program resembles that shown in the figure on this slide. At this point, I'll provide a quick demonstration of the cube program. So I'm going to run the cube program using the -geometry option, again in order to force the window to be placed at a particular position on the display. When I run the program, it draws a cube with the faces of the cube having a variety of different colors. And there's a small white sphere that's drawn right here, which is indicating the position of a light source. So there's a light shining on this object, or shining on the cube. This application can handle resize events in order to maintain the aspect ratio of the cube. So no matter how I resize the window, you'll notice that the aspect ratio is maintained. I can rotate the cube in various ways by using the left, right, up, and down arrow keys. So this is the right arrow, left arrow, up arrow, and down arrow. And then the only other thing we can do, we can quit the program by typing lowercase q. If I rerun the program and provided an extra dummy argument that's ignored, it will draw things using a orthographic projection rather than a perspective projection, and this looks very unnatural. If you look at the shape of the cube, something seems just not quite right. And the reason why is the human visual system sees the world in terms of a perspective projection, so if we use an orthographic projection, things just don't look quite right. Now I'm going to give a walkthrough of the source code for the cube program. This program consists of a single source code file called cube.cpp, and this is the file that we're looking at right now. So to begin with, there's some global data that's used by this program. The first variable is called ambient light, and this is the color for the ambient light in the program. Ambient light is just the background level of light that's basically always there. The color here, the RGB values are each 0.25, so this is going to be kind of a darkish gray color. Then the next variable we have is diffuse light. This is the color for the diffuse light source that we're going to set up. And the color, the RGB components are all equal, so this is going to be a shade of gray, except it's going to be closer to a white kind of color, a little bit dim white. Then we have this variable light position. This is the position of the light source that we're going to be setting up later, expressed in homogeneous coordinates. Since the last component in homogeneous coordinates is 1, this corresponds to the physical point in space 0, 1, 1. We have two global variables, theta x and theta y, which are used to specify rotation angles used in the animation or movement of the cube in the scene, because we can rotate the cube. The next global variable we have is called perspective, and this is just a true or false Boolean value which indicates whether a perspective projection should be used or an orthographic projection. The orthographic projection is really just for illustrative purposes. It's not a good idea to use, as you'll see, as it doesn't really look very good. But for just interest's sake, this functionality is provided by the program. Now I'm going to skip down to the main function to begin with. So if we go to the main function on line 278, first thing we do is we initialize some constants, win width and win height, which are the nominal window width and window height used by windows created in the program. Then we call glut init to initialize the glut library, and it passes argc and argv to this function in order for any glut related command line options to be extracted out and processed, such as the minus geometry option. Then we check to see if argc has any additional parameters, or if there's any additional command line parameters that are provided to the program. In other words, if argc is greater than 1. If this is the case, then we disable perspective projection and use orthographic projection instead. So this just gives us a way to choose between perspective projection and orthographic projection. Then if we continue on, the next thing we do is we initialize the display mode. So we're going to use double buffering, RGBA, so RGB with alpha. Actually, this program doesn't really use alpha, so we could get rid of the alpha. And we specify depth buffering as well. Then we specify with glut init window size the nominal window size for any windows we create. Again, this size is only a nominal size. It doesn't have to be respected, so you always have to check to see whether the window size that you actually got was the window size you requested, because the system can always ignore you and give you a different size from what you asked for. Then we proceed on to create the graphics window for the program by calling glut create window, and we pass to it a string which typically appears in the title bar of the window decoration added by the window manager. Essentially, this is the title of the window. Then we register some callback functions. We call glut display func to register our display callback function display, which appears on line 134 and we'll talk about later. Then we call glut reshape func to register a reshape callback function for handling window resize events. And the function that we have that handles this is called reshape, and it appears on line 194, and we'll talk about this function later. Then we call glut keyboard func to register a keyboard callback function, in particular the function keyboard, which appears on line 238, and we'll talk about this function later in more detail. Then we register a callback function using the glut special func. This is a special keyboard callback function, and the function is called special, and it appears on line 251, and we'll talk about this function as well later. Then we set the clear color to RGB values of 0, which correspond to black, and the alpha value is 0, which is transparent. But again, we're not using alpha in this program anyway. Then we set up some parameters relating to lighting. We're going to have a single light source. Well, before we get to the light source, first we set the ambient level of light, or the color for the ambient light. This is the global variable ambient light that was introduced earlier. So this is setting the kind of the background light level and the color that's associated with that light level. Then we set up our one light source that we have, light source 0, using GL light FV. And this is saying, the first parameter is saying that we're setting light source 0, we're setting the diffuse component of the light source, and this is the color of that light source, which is our global variable that we discussed earlier. In order to use the light source, you have to actually enable it, so we call GL enable to enable light source 0. Also, in order to have any lighting calculations performed by OpenGL, we have to actually enable lighting calculations, so we enable the GL lighting option, which turns on the lighting calculations. And proceeding on, the next thing we do is we call GL color material, and GL enable, and these two function calls, what they're doing is they're causing the properties, the color properties, to track the colors associated with the current color that's set when you establish the vertices by calling GL vertex for the different polygons in the faces of the polygons that you're actually drawing. Then we call GL enable and we specify we call GL enable and we specify GL depth test, which turns on depth buffering, or Z buffering as it's sometimes called. This is what allows you to accomplish hidden surface removal or hidden object removal. Then we call GL enable to enable the face culling. Essentially what this will do is it will disable drawing the backside of faces. In this particular application, we don't care about drawing the backside, so we can save computation by not bothering to do any of the computation for them. Then we call GL front face, which specifies the orientation for front-facing faces. It tells OpenGL which side of a face is the front. Then we call GL enable, specifying GL normalize, which says OpenGL should automatically adjust normals to have unit norm. Normally, if you don't specify this option, then OpenGL will assume that all of the surface normals that you provide have unit length. If they don't, though, then the lighting calculations will be wrong because they assume that everything is normalized. So if you don't have your surface normals normalized, then you should use GL normalize and turn this particular option on. Then we call glut main loop to enter the main event processing loop inside the glut library, and again this function never returns, so we never actually hit this return statement in main here. So that's our main function. Now if we go back up toward the top of the file, line 35, we'll look at the draw axis function. This draws the X, Y, and Z axes that appear when the program runs. So first we call GL begin and we specify GL lines because we're going to draw a bunch of line segments. And the first chunk of code here is going to draw the positive x-axis, so we specify an RGB value of 100, which corresponds to red. Then we specify the two endpoints of the line segment using GL vertex. The first endpoint is the origin, 000. The second vertex is 200 along the x-axis. And then we do a similar thing for the y-axis, except in this case we use a different RGB value. So in this case we use 010, which corresponds to bright green. And then we specify the two endpoints of the line segment we're drawing. And then we draw the z-axis here. First we specify the color. In this case it's 001 for the RGB value, which corresponds to bright blue. And then we give the two vertices. And then we're careful to call GL end, because again every GL begin has to be matched up with the GL end, otherwise you're going to have problems. Then if we continue along here, we have the function that actually draws a cube called draw cube. This is the main shape that's drawn in this particular program. And most of this is table driven. We could write the function with like many function calls specifying vertices and colors and normals and so on, but it's easier to put things into tables, and then it greatly simplifies the code. So the first table here, or first array, is basically the vertices for the cube, and there's 8 of them. Then we have the indexes of the different vertices for the faces in the cube. There's basically 6 entries with 4 vertex indexes per entry. The 6 entries in the table correspond to the 6 faces in the cube. Then we have the surface normals for each of the faces, so there's 6 entries, basically the X, Y, Z component in each entry, and then there's 6 entries for the 6 faces. And then we have the colors for each of the faces, basically a reddish color for the first 2 faces, a greenish color for the next 2 faces, and a bluish color for the remaining 2 faces. And then we have the part that actually does the drawing. And because everything's nicely put into tables, the code that actually does the drawing, this code here, is much shorter than it otherwise would be if we didn't put everything into tables. So basically we call GL begin first, specifying GL quads as a parameter, so we're going to be drawing quadrilaterals. And then we loop over each face in this loop here, the outer loop. And then for each face, what we do is we specify a normal for the face using GL normal. And we look up in our table of surface normals what the XYZ component is for the normal for the face that we're going to draw. Then we use GL color to specify the color for the face that we're going to draw. Again, we're looking up in the table from the tables up above. And then we loop over each, in this inner loop here, we loop over each of the vertices for the particular face that we're drawing, and we call GL vertex for that vertex. And then at the end, we're very careful to call GL end, because again, every GL begin has to match up with a GL end. So this actually draws the cube. And if we proceed further down here, I want to look first at the reshape function on line 194. This will be one of the first callbacks that's invoked. Again, the reshape callback function is guaranteed to be invoked before the first display callback for a particular window. So the reshape function, again, it is given two parameters, which is the width and height of the window. So if the window is resized, this will correspond, the width and height will correspond to the new window size. If it's the very first time it's being called just after a window has been created, this is going to be the initial window size that was actually chosen. And the first thing we do is we compute the aspect ratio for the actual window so that we can adjust how we display things so that aspect ratios are preserved, so circles look like circles and not ellipses and so on. And squares look like squares rather than rectangular prisms. Then we set the viewport using GL viewport, which in this case is going to specify to draw to the entire window. Then we set the current matrix to the projection matrix using the GL projection parameter here, and we load the projection matrix with the identity matrix. And then depending on whether the global variable perspective is set, remember this global variable determines whether we use a perspective projection or an orthographic projection. Really, this program is only meant to be used with a perspective projection because an orthographic projection looks very strange and very unnatural. But just to allow you to see the difference between these two things, the program supports both. But really the interesting case is the call to GLU perspective, which is the thing that sets up the perspective projection by multiplying the current projection matrix times a perspective projection associated with these parameters here. Or for example, the last two parameters are the near and far clipping plane parameters. And then this else clause just sets things up for an orthographic projection. But again, you probably wouldn't want to use an orthographic projection because it produces a result which looks very unnatural. Then we set the GL matrix, or use GL matrix mode to set the current matrix to the model view matrix, and then we load it with an identity matrix. And then we apply a transformation that creates the effect that we're looking at the scene. In other words, the eye or camera is positioned with respect to the parameters specified here. It specifies like the XYZ position of the eye, and then the orientation of the eye, and what the up direction is, and so on. Then next I want to look at the display callback function, which is on line 134. So this is the function that handles the actual drawing, or generating the graphics output. So the first thing we do is we call GL clear, and we specify to clear both the color information and the depth information. And again, you almost always will want to clear both of these things unless you're doing some more advanced sort of stuff. Then we set the position of the light source for light source 0. So the first parameter is saying we're setting things for light source 0, we're setting its position, and the position is specified by this global variable which we talked about a little bit earlier. Then we set the current matrix to the model view matrix using GL matrix mode. So any subsequent operations on the matrices are going to be applied to the model view matrix. And then the first thing that we do in terms of drawing is we draw the coordinate axes. So, but in order to make the coordinate axes always appear the same no matter what, in other words, independent of lighting, first we disable lighting before we draw the axes. So lighting calculations won't be involved in the drawing of the coordinate axes. So this line here is disabling the lighting. Then we call the function draw axes that we've already talked about to draw the XYZ axes. Then we re-enable lighting after we're done so that lighting calculations will be used in subsequent drawing operations that we do. Then the next thing that we do is we draw a sphere to indicate where the light source is in the scene. So we call GL push matrix because we're about to apply some transformations to the coordinate system, and we want to be able to restore things back to the way they were before this point. So we push the current matrix onto the stack. Then we apply a transformation which will translate the coordinate system so that when we draw the coordinate axes at the origin, or sorry, when we draw the sphere that represents the light source at the origin, the sphere will actually be positioned at the position of the true position of the light source, because we've translated the coordinate system before drawing the sphere. We want the light source always to appear the same independent of lighting, so we disable lighting before we draw it using GL disable, specifying the parameter GL lighting. So this turns lighting calculations off. We specify for the color of the sphere that we're about to draw to be white. RGB values all equal to 1, which is corresponding to bright white. Then we use glut solid sphere to draw a sphere, and then these parameters here specify basically how accurate the polygon mesh is that's used to represent the sphere. Then after we're done, we re-enable lighting because we want subsequent drawing operations to use lighting. And then we call GL pop matrix to undo the transformations that we've applied, namely the transformation up above here where we do a translation, so that not everything is going to continue to be translated after this point. Then next we draw the cube, and in this case we draw the cube with lighting enabled. So when we're drawing the cube, we don't disable lighting in this case. So we call GL push matrix again. And then we apply some transformations here. Basically what we're doing is we're doing a rotation about this axis of rotation with the vector 0, 1, 1, a rotation about this axis here, which is the y-axis 0, 1, 0, and a rotation about the x-axis 1, 0, 0 by the amounts that are specified by theta x, theta y, and theta z, which is theta x plus theta y. So this sets up a bunch of rotations. Then we draw the cube. The cube is always drawn at the origin with a certain scale and a certain orientation, but because we've rotated the coordinate system before we draw the cube will actually appear rotated. And then after we've drawn the cube, we call GL pop matrix to restore the coordinate system that we had before we called push matrix up above. And then the last thing that we do is we call glut swap buffers. Again, this is really important. Since we're using double buffering, all of the drawing that we're doing is into a buffer that the user doesn't see. In order to make the changes that we've drawn into this buffer visible, we have to call glut swap buffers. If we don't call this function, the user will never see any of the graphics output. We'll just be drawing beautiful graphics into a buffer that nobody can see. So the next function I want to talk about is the keyboard callback function. This is on line 238. So again, the keyboard callback function handles key presses, regular keys on the keyboard, like the letter A, for example. The parameter key that's passed in is the character that was typed. X and Y are the mouse position, which in this program are ignored because we don't have the mouse position somehow affecting how we interpret the meaning of a key. So X and Y are ignored. And the only key that we interpret is the lowercase q character. And if this is typed, we just exit the program. So Q is used to terminate the program. And then the last callback function we have is a special keyboard callback function. This is used to handle keys like up arrow, down arrow, and so on, page up, page down. In this particular application, we only use the up, down, left, right arrow keys. So again, the parameter that's passed in here, this int value, is a value indicating which key was pressed. X and Y is the current the position of the mouse at the time that the key was pressed. And in the case that the person types the left arrow key, we adjust the theta x parameter by subtracting 5 from it. And this is going to affect the rotation of the cube. So because changing theta x changes what the graphics output would look like, and GLUT has no way of knowing that what we've just done has changed the appearance of the output, we have to force a display event to be generated ourselves. So to do this, we call the function GLUT post redisplay, and this forces a display event to be generated. Because again, if we didn't do this, the GLUT library has no way to know that we've just changed theta x and somehow this affects what the graphics output looks like. It doesn't know this, so the only way that we can force the graphics output to be redrawn is to generate a display event ourselves. So this is why we're calling GLUT post redisplay. Again, a very common mistake when writing code is to forget to call GLUT post redisplay, and if you don't do this, then none of the changes that you've drawn will actually ever be displayed. Then if the user types the right arrow key, then we adjust theta x by adding 5 to it, and then we call GLUT post redisplay, so the result will actually eventually be displayed when our display callback handler is invoked. The down arrow key will cause theta y to have 5 subtracted from its value, and then we call GLUT post redisplay to generate a display event so that the output will actually be redrawn. And then an up arrow key will cause theta y to have 5 added to it. Again, this affects the rotation of the cube, and therefore we need to call GLUT post redisplay so the output will be redrawn. And that's basically the whole program. Now we consider an example program called wireframe that utilizes both the OpenGL and CGAL libraries. The program is essentially a very simple mesh viewer, and with this program the user can view a polygon mesh as a wireframe. The mesh can be rotated, scaled, and translated, and there's a few other things that the user can do. And the graphics output for the program resembles that shown in the figure on the slide. At this point I'll provide a quick demonstration of the wireframe program. So when I invoke the wireframe program, I'm going to use the minus geometry option in order to force the window to be placed at a particular position on the display. The minus geometry option is actually parsed by the GLUT library itself. And depending on the command line arguments for the program will either use a built-in mesh or read a mesh from standard input. And with the usage that I have here, it's going to use the built-in mesh. So when I run the program, it renders the mesh as a wireframe. I can use the left mouse button. Holding the left mouse button down and dragging, I can rotate the mesh. So I'm rotating here by using the left mouse button and dragging. I can use the middle mouse button and dragging to scale the mesh. I can either zoom in or I can zoom out, like what I'm doing here. I can also press the right button down and drag in order to translate the mesh to the left or to the right, up and down, and so on. And notice that when I resize the window, the aspect ratio is maintained. Again, this is not happening magically. The application properly handles the fact that the window is being changed in its size and adapts how things are drawn in order to maintain the aspect ratio. And we can also quit by typing Q. Due to the length and complexity of the wireframe program, it's not practical to provide a walkthrough of the source code for this program in this presentation. The source code, however, is quite well documented, so you can read through the source code on your own and use the comments in the source code in order to assist you in understanding how the code functions.